Now what about a 1D case? We will quickly run through the same procedure, but now we need to ask ourselves the question, how many states per unit energy per unit length, okay, in a 1D material. Okay, the 1D material does not have volume or area, it is just got length, and we follow the same set of questions. How many solutions of Schrodinger's equation per unit length in K space? Okay. And now we have only a 1D box, we are only interested in a 1D box, and we only have, so let us say this is the x direction, the box has got length Lx, and we are only have got a Kx space, there is no Ky, there is no Kz, and there is only a Kx space. And the wave function for a 1D box is simply this, and that is my Kx term, which is quantized with the quantum number nx, and therefore in this space I have, you have your pi by Lx, 2 pi by Lx, and so on. Okay. And if you look at the number of solutions per unit length of K space, okay. First, so these are my unit cells now. So that is one unit cell, that is the second unit cell. Okay. If you look at the number of solutions per unit cell, each cell has got 2 solutions. There is one solution on this end and one solution on that end. There are 2 solutions, but each solution is shared by 2 unit cells. So if you look at this solution, for example, it is shared by this cell as well as this cell, right. So each cell is just a line, it is just this line segment, okay, connecting these 2 discrete points, and these discrete points are the solutions to Schrodinger's equation. So each solution is shared by 2 cells, and therefore there is one solution per unit cell. And what is the length of the unit cell? The length of one unit cell is pi by Lx. Okay, so the length of this unit cell is this length here, which is pi by Lx. So the number of solutions per unit length is going to be one solution divided by the length of the unit cell, which is Lx by pi. But now once again we need to make our correction. Okay, so let's deploy our correction terms. We have these correction terms in the case of 3D and 2D. So Lx by pi, but then we are double counting for n. Okay, for nx could take plus and minus values, so we need to divide by half. Okay, but then there are also 2 spins. Okay, and therefore this is the correction term. So the correction term is simply 1, and therefore your initial guess on the answer was right. So there are this many solutions to Schrodinger's equation per unit length in K space. And now the next question, how many solutions to Schrodinger's equation between k and k plus dk? So now let us extend our kx. Okay, you have this massive grid of points sitting on this line. Okay, it is a 1D case, so we only have one dimension, but you have so many points. And then so where is my k? My k is going to be this long, and my k plus dx is there. Okay, so what I am interested in is the number of solutions in this region, and this region has got a length of dk. So how many solutions exist in this region between k and k plus dk? So that is my question. Okay, so k now is simply kx, there is no ky or kz, so k is simply kx, and that is k plus dk, and this is k, and the region between them has got a length of dk, and we are trying to find out how many states exist between k and k plus dk. Now the number of states per unit cell was already this, right, it was Lx by pi per unit length. So there are these many solutions per unit length, and we want to know how many solutions in this region of dk. For a length of dk, how many solutions exist, and the answer is Lx by pi dk. Okay, so there are dk into Lx by pi states or solutions to Schrodinger's equation, solutions in the region between k and k plus dk. Okay. So, that is the answer we are looking for. And now the next question is, of course, convert everything to energy. Okay. So, now we know that there are dk Lx by pi solutions between k and k plus dk. Now, how many solutions exist between E and E plus dE? So, we convert all the terms from k space to E space to energy E, and we use the same set of relations. Okay. The only thing is this time we only have a dk term. Okay. That's so dk is related to E in this manner. Okay. So, Lx by pi dk is simply Lx by pi into this particular term here, which is your dk, and therefore, there are these many solutions. Okay. So, there are Lx by pi into, we can cancel some terms off. So, you have m power half e to the power minus half dE by 2 power half h bar. So, you have these many solutions present between E and E plus dE. Now, of course, the next question is we want to get to per unit length, therefore, how many solutions per unit length? Okay. So, we have these many solutions between E and E plus dE, and the length of the box is Lx, therefore, that divided by this is the number of solutions between E and E plus dE per unit length of your semiconductor. And finally, to get to the density of states, we need to get a per energy count. Okay. So, how many states are present per unit length per unit energy? So, we once again divide by dE, we get rid of the dE term, and you have this little answer here, which is the density of states for a 1D material. So, there are m power half e to the power minus half 2 power half, that is the square root of 2 h bar pi states per unit length per unit energy in a 1D material. So, how does the density of states vary with energy for a 1D material? It varies as e to the power minus half. So, you see a nice trend here. So, for a 3D material, you saw that the density of states was proportional to e to the power half. For a 2D material, the density of states was proportional to e to the power 0, or in other sense, in other words, it was not dependent on E. And for a 1D material, the density of states is proportional to e to the power minus half. Okay. So, that is how it varies from 3D to 2D to 1D. So, what is the density of states for a 0D material? For a 0D material, you have neither a set of points in kx nor ky nor kz. You only have one solution, probably just one point in k space, and therefore, your density of states is simply a Dirac function. Okay. You have states at one particular energy. So, if you wish, this could be written as at one particular energy level, and you have say 2 spins, and therefore, that is permitted. Okay, to finally summarize the the concepts on the density of states, we looked at 3D materials, wherein we found that the density of states depended on the e to the power half, that is, it varied with the square root of energy. For 2D materials, the density of states did not vary with energy at all. So, you could call it as it varying as e to the power 0. For 1D materials, it varied with e to the power minus half, and for 0D materials, which are similar to quantum dots, it is just a delta function of the energy. There is just one or two energy states, and the 2 is to account for the 2 spins. Now, in this course we will focus mostly on 3D materials. Okay. So, and therefore, this is the density of states picture that is of great use to us. So, we have our semiconductor, which has got a valence band and it has got a conduction band. There is an energy gap, okay, so that let us call that Eg, and then you have states in the conduction band, so above the conduction band edge, and you have states below the valence band edge. Okay. And the density of states, which is the number of states per unit volume per unit energy, varies as E minus Ec to the power half. So, this is like a square root behavior. Similarly, here too you have a square root behavior with the density of state distribution. And inside the gap, as long as your semiconductor is very clean, as long as it is a perfect crystal, you have no states. So, if you look at this density of states here, it is 0, and you have a density of states varying as the square root of energy above and below these conduction band edges. So, this picture is of great use to us throughout this course, and it would sort of help gather some amount of intuition. It's helpful to visualize this very clearly. So, moving on, so what we have counted for now is the number of states available, okay, and the electrons can now start occupying these states, okay, and what we are trying to get at ultimately is the number of electrons that are available for conduction, because ultimately we want to measure the current voltage characteristics. Now, we know the number of states, but we now need to find out as to what the probability of occupancy of those states are. So, the probability of finding an energy state, okay, so which is basically a solution to Schrodinger's equation. So, if you have a state at some energy E, there is a certain probability that the state is occupied with an electron, and that probability is defined by this variable, or the symbol f of E. Okay. It depends, it is a function of energy, so it depends upon the energy, and we call it f of E. So, what is f of E? So, since electrons are fermions, okay, which means that these are particles that obey the Pauli's exclusion principle, you find that f of E is defined by something called as a Fermi-Dirac distribution, okay, and it turns out that f of E is defined by this function here, which is 1 by 1 plus e to the power E minus Ef by kT. In this function that you see, your k is your Boltzmann's coefficient, T is the temperature, and Ef is something called as the Fermi level. Okay. So, it is an energy level which has got a special implication in semiconductors, and it is called as the Fermi level. So, it is a technical term, and we will continue using this, and we will typically use the symbol Ef to denote the Fermi level. Now, what do you mean by the Fermi level? So, if you were to take this function, okay, f of E, and plot it here, okay, so I have energy on the y axis and I have f of E on the x axis. So, at t equal to 0, what is this function? It is going to be 1 by 1 plus e to the power E minus Ef by 0. Okay. So, this means it is going to be a very large number, but depending on whether E is greater than Ef or E is less than Ef, this number could be very largely positive or it could be very largely negative. Okay. So, suppose E is greater than Ef. Okay. So, Ef is some energy level. So, for now let us just mark it somewhere, let us just call that Ef. So, this is the energy scale, and let us say E is greater than Ef, which means that this quantity is positive, and as the temperature approaches 0, this number is a very large positive number which starts heading towards infinite. Okay. So, as t approaches 0, you have 1 by 1 plus a term approaching infinite, okay, if E is greater than Ef. So, which means that this value is going to be heading towards 0. Therefore, for all energies at t equal to 0, for all energies above Ef, the value of the Fermi function or f of E is 0. So, you can see that this is going to be the Fermi function, it has got a value of 0. Now, the moment E becomes less than Ef, okay, you have 1 by 1 plus e to the power minus a very large number. Okay. So, this number starts heading towards infinite as t tends to 0. So, this value now starts heading towards 1, because e to the power minus infinite is going to be 0 and you have 1 by 1 which is 1. So, therefore, for all values of energy less than Ef, okay, at t equal to 0 Kelvin, the function takes a value f of E is equal to 1, and at E equal to Ef. So, when you have E is equal to Ef, okay, so when you have E equal to Ef, the Fermi function has got a value of 1 by 1 plus e to the power 0 by 0. So, in some sense it is undefined. So, we need to take limits. So, let us say t is heading towards 0. So, you have 1 by 1 plus 1 by 1 plus e to the power 0 which is 1, and therefore, this function tends to 1 by 2. Okay. So, at E equal to Ef at t equal to 0, you have the function actually somehow making the switch from the value of 1 to the value of 0, and therefore, you can say in the limit the value of this function is half. Okay. So, this is the Fermi function, this is the behavior of the Fermi function at t equal to 0. So, what does this say? Since f of E is the probability as to whether an energy state is occupied by an electron or not, f of E equal to 1 implies that the electron definitely occupies that state, and f of E equals to 0 implies that the electron definitely does not occupy that state. Okay. So, what this picture tells you is that at t equal to 0, any state that is below Ef has got a guaranteed chance that an electron will occupy it. So, if a state exists here, it is definitely going to be occupied by an electron. And at t equal to 0, what f of E tells you is that if a state exists above Ef, it is definitely not going to be occupied by an electron, which means that the state is vacant, or in other words the state is definitely occupied by a hole. Okay. So, this is the meaning of f of E. Now, as temperature increases, okay, so this is what happens at 0 at t as t approaches 0 Kelvin, right. So, t approaching 0 Kelvin is t equal to 0 Kelvin is not possible, okay, that is it is against the laws of thermodynamics. So, let us say let us take a more realistic case where you have a temperature T1 that is greater than 0. Okay. So, now what happens to f of E? So, you will find that if you were to plot for some temperature T1, if you were to plot this function, you will find that it has got this particular shape. So, it is deviated from its t equal to 0 shape, and it has got a shape that looks like this. So, what does this say? As E goes much less than Ef, okay. So, 1 by 1 plus e to the power E minus Ef becomes a significantly negative number, okay. So, let us call it x for all practical purposes, okay, just for the sake of arguments here. So, as x tends to, so x is your E minus Ef, okay. So, as E becomes less than Ef, okay, if E becomes less than Ef, x becomes a negative number, okay, and if you have an exponent of a very largely negative number, it is going to be much less than 1, and therefore, this function tends to 1. So, as you head very far away from Ef and below Ef, the value of the function heads towards 1 asymptotically, okay. And equivalently, as you head above Ef, and very far away from EF. Okay. So, as you go to higher and higher energies. Okay. X is a positive number that is continuously increasing, and this term dominates this term, and you will find that 1 by a very large number tends to 0, and therefore, this function here starts heading towards 0. But at E equal to EF, okay, at E equal to EF, your x is equal to 0. Okay. So, x is equal to 0, and which means that this term here is equal to 1, and therefore, at E equal to EF, the value of the function is 1 by 2. Okay. So, irrespective of the temperature, you will find that when my E is equal to EF, the function takes a value of half, or in other words, the function crosses this point, this coordinate of the x coordinate being half. This plot, if you plot energy versus f of E, you will find that for any temperature you will always, the function will always cross this coordinate of half comma EF. Okay, that is EF as being the energy and half being the probability. So, at temperature T2, the function deviates further. Okay, it moves further away from the T equal to 0 condition, and it sort of begins to smoothen out. Okay, you will see that the occupancy probability above EF begins to increase, and the probability of non occupancy below EF also begins to increase. Okay. So, that is the nature of f of E, and this nature is very important. Okay. So, we have identified the number of states defined by the density of states, and what we are doing here is we are trying to find out what the probability is that those states are occupied by an electron. Okay. So, let us look at some of the key properties of this probability. Okay. So, which is called as the probability of occupancy of the electron defined by f of E. So, what are the key points? Okay. So, these are some key elements to remember. So, f of E is the probability. Okay. Please do not mistake it for a density function, it is not a density function. Okay. So, if it were to be a density function, then f of E dE would have to be the probability, and which means that this summed over all the states should be equal to 1, which is clearly not the case. So, please do not mistake it to be a density function. F of E is the probability. Okay. And if it is a probability, what is the random variable? The random variable is as to are the two conditions or the two states, right. Given an energy level, is it occupied by an electron or is it not occupied by an electron? Okay. So, this is these are the two possibilities. It is like a coin toss with a head and tail being the two outcomes. So, here you have two outcomes, which is given an energy level, is that energy level occupied by an electron. So, it is, let us say, occupied is one state and not occupied is the other state, and the probability that it is occupied is given by f of E. So, which implies that if f of E is the probability that it is occupied, what is the probability that it is not occupied? It has to be 1 minus f of E, okay, because the probability of the summation of the probabilities of these two states occurring has to be equal to 1. It has to be either this or that, there cannot be a third option. Okay. So, that is the second point, which is the random variable is the occupancy or non occupancy. Now, what is EF? EF is the Fermi energy level, is the Fermi level. Okay. So, it defines an energy at which f of E takes a value of half, and we already discussed that. So, if you look at the value of this probability of occupancy, it takes a value of half at E equal to EF. Okay. And we already saw that the probability of non occupancy, that is given an energy state at a level E, the probability that is occupied by an electron is f of E, and therefore, the probability that is not occupied by an electron is 1 minus f of E, which is what? Which is simply saying that this is the probability that it is occupied by a hole, okay, which is a vacancy. So, f of E is the probability that a state is occupied by an electron, and 1 minus f of E is the probability that that state and at energy level E is occupied by a hole. Okay. And then finally, if E minus EF, okay, so if this term is much larger than kT, okay, so I will not say much larger, let us say it is greater than 3 kT, which is basically implying that this value is much greater than 1. So, if the sum of the denominator can be approximated to 1 by e to the power E minus EF by kT, then this becomes the Boltzmann distribution. Okay. So, this is your Boltzmann distribution, which is simply saying that as the energy goes up, the probability that you will find an electron goes down exponentially. Okay. Now, if E minus EF is approaching values of kT, you cannot what do you say, simplify this denominator, and you need to take into account the entire Fermi function value. Similarly, if E minus EF is much less than kT, okay, so this was the case when E minus EF is much greater than kT. If E minus EF is much less than kT, 1 minus f of E, which is basically the probability of occupancy by a hole, approaches the Boltzmann distribution, which says that the probability that a hole occupies an energy level E goes down exponentially as E goes much less than EF. Okay. So, that is basically these approximations, and we will use these approximations quite a lot because it helps simplify a lot of the mathematics and the calculation. Now, so this is all we have to say about the Fermi function and the Fermi level and the Fermi distribution. But so let me tell you a little bit more, let me give you some intuition about this. Okay. So, a very nice way to imagine it, okay, it may not be the perfect way, but it is an intuitive way to imagine it, is to consider a bucket of water. Okay. So, let us say you have a bucket and you have got some water, you fill these water molecules one by one, all these water molecules are filled up, and you have a water level that is still this point. Okay. Now, suppose I ask you the question. So, let us say this is all the air and that is the water as you see it. Now, suppose I ask you this question as to where is the air water interface. Okay. Very intuitively somebody might point out to this layer here. Okay. But does this mean that there are no water molecules above this? Okay. What is the probability that I will find a water molecule below this level, at this level, and above this level? Okay. Suppose I ask you this question. If the temperature T is greater than 0, you will definitely find some water molecules above this level. It is just that they are going to be much sparser as compared to the number of water molecules I will find below this level. Okay. So, this level can be imagined to be what is called as the Fermi level. Okay. It is the, in some sense, the highest energy level that could be occupied by all these species at T equal to 0, okay, where the probability of occupancy is still not 0, okay, it is equal to half at T equal to 0. Above this level at some temperature T greater than 0, you will find that the distribution of water molecules, that is the concentration of water, goes down exponentially. It is like the Boltzmann's distribution. Okay. And below this you have a much larger probability of finding water molecules. And if you imagine the surface, okay, let us say these are the water molecules at the surface. Okay. You can see that it's shared between the air and water boundary. So, you can sort of imagine that to be your probability being half. Okay. So, it is a very hand wavy but very useful analogy to think of what the Fermi level is. Okay. And we will come back to this bucket of water examples every once in a while. So, now if this is the Fermi level, then what do you mean by the density of states with regards to this water bucket analogy? So, the best the best parallel to the density of states is the shape of the bucket. Okay. So, if you have a bucket that is shaped like that, you have a different density of states distribution, and the water molecules need to fill all these states, and the Fermi level sets itself at some particular point. Okay. On the other hand, if you have a bucket like this, it has got a very different density of states, and for the same number of molecules the Fermi level will be located elsewhere. So, this analogy cannot be used throughout. I mean, it is just a very hand wavy visualization of what we are talking about, but nevertheless it is useful. Okay. So, that is the key element about the Fermi function. Now, some of you might wonder as to where this f of e came about. Okay. So, although it is not a part of this course, I can post some notes online, probably I will give you a link to where you can find these notes. And essentially f of e comes about by finding out the best possible way to distribute, say, n electrons among s different states. So, these are n identical particles distributed in say a set of empty states or seats. Okay. So, that is if you find the many methods to do it, the best possible way where you can maximize or find the best possible options is what defines your f of e. Okay. So, that is a bit of statistical mechanics. All right. So, what do we have? We have the number of states, which is defined by the density of states. Okay. So, the density of states tells me how many states are there per unit energy per unit volume, and we have the probability that those states are occupied by an electron. So, using these two, we can now begin to count the carriers. Okay. So, we are ultimately interested in counting the number of electrons available for conduction. Okay. Most particularly, if this is the conduction band edge and this is the valence band edge, we are interested in the electrons in the conduction band, okay, and the holes in the valence band. We are not so interested in the electrons in the valence band. There are many of those, because these are all these are all bound to all the different silicon atoms. Okay. There are many electrons in the valence band, and equivalently there are many holes in the conduction band. It is largely empty. Okay. So, we are not interested in the holes in the conduction band and the electrons in the valence band, but we are very interested in the electrons in the conduction band and the holes in the valence band, because these are the species that are going to constitute my current through these devices, and ultimately I want to get to a point where I can start to define my current voltage characteristics in all these devices. Okay. So, always remember, we are interested in the electrons in the conduction band for E greater than EC and holes in the valence band, that is E less than EV. This is of interest to us, and we want to establish a method to count these. Okay. So, how do we count? How do we identify the number of electrons, or more particularly the number of electrons per unit volume? Okay. So, the number of electrons per unit volume, which we will call as the electron concentration. Okay. It is not per unit area right now, it is per unit volume, and the number of holes per unit volume, that we will call as the hole concentration. So, how do we identify these two? Okay. So, if you ask yourself this question, what is the number of electrons per unit volume, which we will define by the symbol n of E lying between E and E plus dE. So, I have two energy levels. Okay. This energy level is E, that energy level is E plus dE, and we want to know how many electrons are present between these two, and we will call that as n of E. It is a function of energy. If this E changes, the n might change. Okay. So, the answer is very clear. So, you need to first know how many states are there for the electrons to occupy. Okay. If there are no states, there can be no electrons, because electrons have to have a state to occupy, because these states are essentially the solutions of Schrodinger's equation. So, you need to identify the number of states per unit volume per unit energy, or let us say the number of states per unit volume between E and E plus dE, okay, which is nothing but the density of states into dE. The density of states is the number of states per unit volume per unit energy, but since we are interested in E between the number of states between E and E plus dE. So, this energy gap has got a value dE. So, it is density of states into dE, which is the number of states between E and E plus dE per unit volume. So, I know the count of the number of states, but it does not mean that all these states are occupied by electrons, because there is a certain probability that the electron will occupy these states, and that probability, as we saw, is defined by f of E. So, f of E into the number of states between E and E plus dE is my electron count, that is n of E. Okay. So, if you were to take a semiconductor that is extremely clean, okay, which means that there are no states in the band gap, okay, there are 0 states in the band gap, and let us say I pick an energy level between E and E plus dE somewhere there at a temperature T greater than 0, and we ask the question as to how many electrons are present between E and E plus dE. Well, the first answer is the number of states, that is the density of states into dE is 0. F of E is not 0, because f of E could be taking a value that is non-zero. So, there is a probability that an electron will occupy that energy level, provided there is a state for the electron to occupy it. Okay. But since our band gap is very clean and there are 0 states, even though f of E is not 0, the number of electrons to be found is 0. On the other hand, if let us say we want to find the number of electrons in some energy level lying in the conduction band, okay, so let us say that is EC. So, that is my EC, and I want to know the number of electrons between E and E plus dE. Okay. So, what do? I need to identify the density of states into dE. So, here I do have a density of state distribution, and I know that it varies as the square root of E minus EC is proportional to this. So, we do have states. So, the density of states into dE tells you the number of states per unit volume in this region, okay, and f of E is the probability that these states are occupied. The probability is going to be low, but it need not be 0 at t greater than 0. Okay, at t equal to 0 it is definitely 0, but at t greater than 0 this probability is non-zero. Therefore, you do have some probability, a very small probability that these states are occupied, and therefore, you can establish a carrier count, and it is these electrons that are going to help you in providing a current through the device. Alright. So, next, if you ask the question, what is the number of holes between E and E plus dE? Okay. So, which means I need to identify P of E, which is the number of holes per unit volume between E and E plus dE. Then again I get the density of states. I need to find the number of states available, that is the density of states into dE, into the probability that these states are not occupied. Okay. F of E is the probability that states are occupied, but the probability that these states are not occupied is 1 minus f of E, and therefore, this is my count of the number of holes per unit volume between E and E plus dE. Okay. So, this is a very useful relation to remember. It is again, it is good to develop intuition with regards to these concepts. Alright. So, now we are interested to find the current, okay, and it is all the electrons above the conduction band edge that are going to contribute to the current, and all the holes below the valence band edge that are going to contribute to the current. Okay. So, we are not only interested in the number of electrons between some energy level E and E plus d, okay, but instead we are interested in the number of electrons from EC, that is the band edge, the conduction band edge, all the way up till infinite, okay, that is all the electrons present in the conduction band, okay, because all these are going to aid my conduction. So, how do I collect or count all the electrons above the conduction band edge? It is straightforward. It is going to be the answer we have obtained in the previous example, which is n of E, okay, but summed over all the different energy levels, right. So, this is n of E and I am going to take a summation, which is basically I am going to take an integral from E c till infinite of f of E into the number of states between E and E plus d. So, if I were to sum all these electrons present in all these little bands from E to E plus d, then I will get my total number of electrons in the conduction band. And if I make use of the Boltzmann's approximation, okay, and I perform this integral, you will end up with a term that looks like this. After you apply the limits, you will find that the number of electrons from E c till infinite turns out to be this value in the case of a 3D semiconductor. Okay. So, you see, firstly it depends on e to the power minus E c minus E f. Okay. So, if I have my E c here and if I have my E f here, okay, and let us say I have my E v here, this distance is important, and the further the Fermi level moves away from E c, the smaller the number of free electrons, and that is clearly understood because this is the probability. Okay, the probability varies like this, and if I were to move the Fermi level away, the probability is going to vary because it is going to take a value of half at the Fermi level. So, my half will appear here instead of it taking a value half there, it will take a value of half at a much lower value of energy, and it is going to take a much smaller probability of occupancy at the energy levels above E c. So, as E c minus E f increases, if that as that gap increases, my electron count is going to start coming down, okay, the free electron count is going to start coming down. Now, this term here is a constant. Okay. Now, this prefactor to this exponential is a constant. M of m e star is the effective mass of the electron, k is the Boltzmann's coefficient, T is the temperature, h is the Planck's constant, and that particular term is typically denoted by a constant symbol. Okay. It is called N c, which is the effective density of states in the conduction band. Okay. So, this is not the density of states, it is not the number of states per unit volume per unit energy, it is the effective density of states, which is basically the number of states per unit volume in all energies from E c to infinite. Okay. So, it is analogous to that measure. Now, similarly, if you want to find the total number of holes in the valence band, because that is what is going to help me carry current, we find that the number of holes in the valence band is the summation of all the holes from E between E and E plus d, but going from minus infinite to E v. So, that is my E v, that is my E c. To find the number of electrons, I needed to find all the electrons sitting from here all the way till infinite. And to find the number of holes in the valence band, I am going to find all the holes sitting between E v and minus infinite. So, I am going to integrate from minus infinite to E v 1 minus f of E, the density of states in the valence band times d E is going to give me a measure that looks like this. So, this is the total hole count in the valence band, okay. And what is that? So, just like in the case of electrons, I have my E v and I have my E f and I have my E c. we found that as this gap increases, the number of electrons in the conduction band decreases, because the probabilities got a lot lower. Similarly, if this gap EF minus EV, okay, so this is EF minus EV, begins to increase, the number of holes available in the valence band will start to decrease. Once again, why? Because 1 minus f of e will start to get a lot smaller if this gap starts increasing. So, and all this happens because f of e has to take a value of half at EF. So, if I move EF around, I change the probability of occupancies in the states above EC and below EV. Now, just like we defined an effective density of states in the conduction band, we can define an effective density of states in the valence band, which is called as NV. So, the number of holes available for conduction are the number of holes between minus infinity to EV, which is the effective density of states in the valence band, which is essentially this constant here, times e to the power EV minus EF by kT. Okay. So, that is the way you count the number of carriers available for conduction.